Hungarian and Thai. But it's not mixed. It's one or the other.
Supposed to try carrot cast. At least I can't combine it with the kind of thing that tell him about let's go there. And he claims that the grass restaurant is fine with them. Not sure that's ever happened.
There's another one, but that one is bad. So that one is one of the other. So that is gross. But I was told that was during other time. I thought it was 6 restaurants.
That was the I had a backpack money. The last one.
The welcome to the back. There you go.
Is that not coming up for you?
That's selected to my
Sharing. Be all right because this works in the class. Sure.
In the worst case, you have it on PDF, right?
Yeah, I do.
And so we can also put it on the in-room.
No,
Oh, okay, now it works. Great. Fingers crossed. We had a lot of technical difficulties last week.
No.
And if that doesn't work, then we can just put it on the main computer, seminar computer here, which does work now. I have double checked
I
that.
feel we should invest money in buying a new machine because this has been almost as long as I've been here, like 10 years.
This is a new machine. That's the
It is.
problem.
Oh,
this is
okay.
brand new,
Okay,
and we
okay,
still
okay.
haven't figured out all the issues with it.
Do I need to go
Let me try doing.
That's why I use the black one.
This is a different cable than last time. I have another cable that may work as well. Let me try my other cable, and if that fails, then
Yeah, so
This works.
this and then it fails.
is it working?
No.
Then let's try this cable. And you want to get your. That's a USB-C to it, yeah.
Right. Okay, that's
So, let's see. Okay, fingers crossed. Hold for 30 seconds.
Yeah, it's already holding for one.
Yeah, it's holding for more than 5. Okay, good.
So there's a trick to it. USB-C to HDMI with this particular cable.
Yeah. Okay. So maybe it's not your cable, not the cable last time. There was some weirdness with like the different protocols.
Yeah.
Okay. Yeah.
Okay, but that says that there's something. Yeah, there's something wrong with that.
Okay. So we
need
need
to
check your
figure out-
HDMI cable afterwards as well.
Yeah.
The one that you took because it was broken. But. And we are right on time. Lovely.
Okay.
Thank you everyone for coming to the very last Analysis and Applied Math seminar of the semester. We are very happy to have Teemu Tyni, who will be talking about stability of inverse problems on manifolds. So take it away.
Thank you, and thank you all for the opportunity to give this talk here. So yeah, my topic will be really stability for inverse problems for some particular class of nonlinear wave equations on Lorentzian manifolds. And this work is joined with Professor Matti Lassas from Helsinki and Toni Liimatainen and Leiker Potential and Machado from Helsinki and Jyväskylä. And I don't know what's your background in inverse problems, so I thought it would be a good idea to tell a little bit about those. So when I speak of direct problems or forward problems, I mean that I'm going from some cause to an effect. So I have something that caused effect, and then I'm interested in measuring what is the effect that it's causing. And in inverse problems, I'm going backwards. So I know now some effect, and then I'm interested in what caused that. So some examples I've listed few, and there are so many more. So perhaps the most famous ones are from medical imaging, where people use EIT, the electrical impedance tomography, or computed tomography, or magnetic resonance imaging, things like that. These are all examples of inverse problems. So maybe enough of that. Today I will speak of this particular problem and to fix the notation. I will be working on n+1 dimensional globally hyperbolic Lorentzian manifold. So what I mean by this is that on my manifold it's a space-time, and this global hyperbolicity just means that there are no closed time-like loops. So if I proceed forward in time, then I can never return back. So time travel is forbidden. And if I look at like the causal future of some point, so you could travel along light like this, you get a light cone, then you take another point somewhere in the future, and you consider this set in between, then these sets should be compact. So this means that there is no singularities in my manifold. So this is just a fancy way of saying that my manifold has no holes and there is no time travel backwards in time. Then for some technical reasons I assume that the metric of my manifold is of this particular form. So the metric is G, which is minus a positive smooth function in beta times a dt squared plus a Riemannian metric H, depending smoothly on the time parameter. And this is not really a restriction on the classes of manifolds that I can consider, because there is a theorem which says that all globally hyperbolic manifolds, the metric can be written in this form. Right. And since I will be speaking about wave equations, I need the wave operator, and it's basically the Laplace-Beltrami operator on Lorentzian manifolds. So it's given in terms of the metric tensor as this sum. So if you don't like working on manifolds, then you could restrict, for example, to the Euclidean case, where this is really just the standard wave operator. So minus dt squared minus the Laplace operator. And I will be working with this kind of particular nonlinear wave equation. So the first line here is just a wave equation. So I have the wave operator acting on u of time and space plus potential term times u to power m. So the second piece here is nonlinear. Then on my manifold I will restrict a little bit. So I will not work on the whole manifold M or N. Rather I will restrict to some compact set in the space direction. And there I will consider a boundary value problem. So I'll set u equal to f on the boundary of the manifold. And for brevity, I'll denote this lateral boundary by sigma. Then, as the initial values, I just set 0. So u at time equals 0 and the partial derivative time at 0 are 0. So this is quite standard wave equation. And the forward problem would ask, so given this kind of equation, find what is the wave that satisfies the equation. And for a forward problem, the properties of this Q are now somehow interesting. So when you vary Q, you are interested in how does that change your solution. Alright, but I'm interested in the inverse problem. So my Q here will be unknown, and I want to determine this Q from some measurements. And the measurements are defined by the Dirichlet to Neumann map. So the DNA map, it's a map between Sobolev spaces. So I take some HS plus 1 Sobolev space where the functions are compactly supported on the lateral boundary and map them to one smoothness index closer Sobolev space HS, where I don't necessarily know are the functions anymore compactly supported or not. And this mapping is defined simply by taking the boundary value, so the wave equation, and mapping that to the normal derivative of the solution to the wave equation on the boundary. So by this partial derivative mu, I denote the normal derivative on the lateral boundary. So this is the setting I will be working on. And maybe I should mention that this is somehow practical. So in reality you can measure this kind of data. So you send waves in, for example, sound waves, and then you measure the pressure that comes back. So that would correspond to measurements of this kind. Right, and now the inverse problem is measure or determine this potential function Q given measurements of the DN map. So just measurements on the boundary. We want to determine something which is inside the domain. So this kind of question has been hugely popular for tens of years now. So I mentioned few examples. So in already 1987, Belishev and Kurilev studied an inverse problem where they were looking at the wave equation with variable wave speed, depends on just position in space, and they wanted to determine the wave speed. And they used something called the boundary control method. And in 95, there's a famous Tatar's unique continuation principle, which was also used for this problem. So already in the 1980s, 1990s, this was studied.
So am I correct? In 1987, they say if you can prove this uniqueness problem, then the inverse problem is solvable. And in 1995, the uniqueness is
I think they solved showed the uniqueness already in 87 using this boundary control method. Yeah, so they used the boundary control method and this continuation principle back then. Yeah, first results in this direction were by this Belishev and Kurilev by boundary control methods. Yeah, but then I jump 20 years forward in time. Then Kurilev, the same person here, Professor Matti Lassas and Günther Ullmann in 2014 studied nonlinear problems. And the important realization was that nonlinear equations are easier than linear equations. And this may be surprising. So these guys used the nonlinearity as a tool to study inverse problems. So there's some extra information that comes from nonlinear equations that is not present there for linear equations. And my goal today is to explain what's the point of nonlinearity and how does it help. So since then, there's been a huge surge of results in this direction. So I've listed few names and there are so many more people studying this. So the nonlinearity, when it was realized that it's helpful, caused a lot of people to join the field. Right, so then it's one thing to consider, can you uniquely recover this measure Q. Of course, uniqueness is important, because if you have non-uniqueness, you make measurement and then you get possibly several results, and then you don't know which one is the correct one. But just as important for practical point of view is how stable is this reconstruction. So when I make measurement, there is inevitably some measurement error. And depending on the error, I should somehow be able to say how good is my reconstruction. So how big errors am I making in the reconstruction process. Right. But there's some things we cannot recover, and this now depends on the space-time that I'm working. So we can only reconstruct things which are causally connected to the measurement domain. So we can only look at things that happen in the future of my boundary and in the past of my boundary. So that picture is like this. So if here is the spatial part of my domain, omega, and time runs up. So here is the lateral boundary, sigma, the domain. Then when I send a signal from a part of the boundary, I send a wave here, it travels along light-like geodesics, and it takes some time before it arrives to the boundary again. So this causes a restriction where I can do reconstructions. So if something happened in the past, there is no way I recover that, but I can still reconstruct things in the future. So I'll denote by W the domain where I do reconstructions. And I decided to copy paste here our full theorem. It's a mouthful, but the principle is quite simple. So suppose I have two potential functions, Q1 and Q2, which are smooth enough, so continuous with derivatives up to order s+1. And the norm in the CS+1 norm is bounded by some constant. Then let lambda1 and lambda2 be the corresponding Dirichlet to Neumann maps. So this is my measurement data. Then if the Dn maps for some particular boundary value are close enough to each other, so their difference is bounded by some small delta, for all sufficiently small boundary values f, then I know that when I do the reconstruction, I recover Q, the difference between these two potentials Q1 and Q2 in the subnorm will be bounded by delta to power sigma. And sigma is some explicit number that we can calculate. So what this now practically says is that when I make measurement error of size delta, then in my reconstructions I make errors of size delta to power sigma.
Let me ask about R.
Sure.
Right, so normally it would be the should normally be from s+1 to s. But now you choose to measure in any R that you like.
Right.
And that's
Yeah.
so the lower R, the more precision you can hope for. Am I kind of correct? You're asking for less. You're asking for fewer derivatives.
Yes.
Am I thinking it the right way?
Yes. So it will be coarser measurement. So I allow bigger errors somehow in the here. Right. So let's see. Oh, I have not written it here. So I think R should be less than S.
It has less or equal. Right?
Yeah, less than or equal. Yes.
Right.
So this could be just L2
Right.
for all I know. So I allow somehow big errors in the measurement.
I'm just trying to be practical, and I think maybe I'm being stupid, but I thought if you want to measure a function in high absolute norms, you're asking for a lot. It's
Yeah,
difficult function.
exactly.
Right?
True.
Whereas if you want to measure the function L2, You're not for too much.
Yeah,
So,
true.
okay, fine.
Yeah, so that's what it says. So we allow less smoothness. And somehow interestingly, it doesn't really matter what the R is for us. So it never appears in the estimates other than in this constant here.
What is M again? What is
M was, oh sorry, I will go back. So M was the
Oh, I see.
power of nonlinearity. And I should emphasize, did I not write it here? That M, I assume, is greater than or equal to 4. So I will write it here. So M, the power of nonlinearity, is greater than or equal to 4. And I will explain why I need this. But,
Just as a sanity check, so the bigger R is, the smaller C is, right?
sorry?
The bigger R is, the smaller C is, right? If C depends on R.
Yes.
Okay.
Yes. Yeah. But I think this one is a little bit interesting. So the more smoothness we want, the smaller this number is, and the worse is the stability.
You want it, the
Yeah.
bigger the better, right? The bigger sigma the better. That's
Yes. Yeah. Yes.
You don't need any information about the support of Q. So what if Q1 could be identically 0 and Q2 could be strictly positive, or Q1 could be changing sign and Q2, you have no need for anything like that.
No, nothing at all.
So you could be comparing a linear equation to the solution to a linear equation to the solution to a nonlinear equation. If Q1 is identically 0.
Yeah, so it's possible, but I think this will force, if Q1 was for example 0, then this would eventually force Q2 also to be 0. But let's see, is this not true? I think this will not work in the linear case.
One
Yeah.
reconciliation of your two things is if you chose one Q to be 0 the other, then the Pearson phenomenon would be very far apart. That's the
Yeah, so-
reconciliation, right? And so then
Yeah, so this-
you will get a result, the result will be very poor because the delta is very big.
Except that what you said is the exact opposite of what he was saying.
Okay?
You're saying that if they're,
Okay, well, trust him.
Yeah, so I think, yeah, but what Gross says is, it makes sense. So if one of them is 0, then probably we cannot make this very small. Can you imagine?
so that's what Spiro said, sorry.
Yeah, 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 yeah. But I'll say this, so this is important, so the nonlinearity really is important. So I can only recover things where this Q lives. So if Q is 0 somewhere, well then I recover well 0 basically. So I mean it works still, but I'm not recovering anything if one of them is 0. I don't know, does it make sense? Right. So the big idea here is to use a method that we now call by higher order linearization. So the trick is to just use some small parameters, epsilon 1 to epsilon n, where m was the power of nonlinearity, in the boundary values. So the same nonlinear wave equation as before, but in the boundary values I put some parameters. So I consider boundary value epsilon 1 times f1 plus epsilon 2 times f2, so on until epsilon m times fm. And if we do this, then the solution of the nonlinear equation can be expanded into Taylor series with respect to the epsilon. And maybe it's a good idea to write down a couple of formulas. So Taylor series contains some functions, bj's and wk's. So we will write here that Vj's satisfy this kind of equation. So box each of the Vj's is 0. So Vj satisfies just linear wave equation over the manifold. Boundary values of these Vj's are the Fj's that I used in the nonlinear equation, and Vj and time derivative of Vj vanishes when the time is 0. So we have 0 initial values, and here on sigma. So these Vj's satisfy completely linear equation where we know everything. So we know the boundary values that we are putting in. Then the W function, it will satisfy this kind of equation where we have the unknown potential Q and then product of these P functions. So V1 to the power K1 and so on, product until Vn to Kn. Wk on the boundary is 0 and the initial values of Wk with respect to time are 0. So the W function satisfies this kind of equation, where once we know these Vj's, then we know the W function. And this piece is now somehow crucial, because this is a linear equation where we know this piece and it contains the unknown Q. So all of this you could consider as a source term, because it doesn't depend on W at all. But that's the main idea. So now if you were to formally differentiate this equation, okay, there will be some higher order terms also.
The higher order in epsilon.
In epsilon, yes. So here the product is such that when you add up together all of the powers of epsilon, you get the power of nonlinearity, and in the remainder, total power in epsilons will be bigger than m, so m plus 1. So now we differentiate this formally with respect to these epsilons. So differentiate with respect to all of them. And let me just show this again. So if we differentiate this with respect to, say, epsilon 1 first, then the only term in this first sum that survives is the term containing epsilon 1. Then I differentiate with respect to epsilon 2, and that kills this term entirely. In the remainder, the powers of the total power of epsilon was greater than m. So when I differentiate the remainder term with respect to epsilons and set epsilon to 0, that kills the remainder. So the only thing that can survive the differentiation is this middle term, and in particular the only term survives is the one where each of these k powers here equals 1.
So I'm a bit confused about this expansion. So the first term is linear in epsilon, and then the next term is epsilon to the m. Why are there no terms in between, like no epsilon square term, for example?
Yeah, I think you'll have to do the calculation. So if you do the Taylor expansion, the middle terms will disappear. I think you have to use this.
Because it's u to the n, right? So you're taking epsilon and raising it to the n. Epsilon
Yes.
n.
Oh.
So,
That's where it's coming from.
the middle terms will disappear.
Oh, okay.
Oh, then if you square, that would, There will be an intermediate, but you
Yeah,
get the record.
okay, my
Yeah.
God.
So there's only one term that survives if I differentiate this now, and
Okay.
where all of the epsilons are 0. But unfortunately, since in practice we would have some measurement error now, so if I measure this u now somehow on the boundary, and there is any error, and I'm setting this epsilon very small, so epsilon would be 0, the measurement error will make the derivative blow up. And I don't want that. So I will not use the literal derivative, but I'll approximate the derivative by finite differences. So here I'm just taking the usual finite differences of the solution u. So it can be written compactly in this form, but really think of this as the standard finite difference operator here. And now in particular, I'm not setting these epsilons to 0 yet. So my finite difference will depend in the end on epsilons, and I want to make a good choice of these epsilons. So that's the ultimate goal that I want to do. So let's see where this now leads. So if I look at the nonlinear wave equation and I apply the finite differences to that, then we just calculated finite differences derivative applying on the function u would give you just the one term, w, and then acting by the wave operator on w, so your wave operator acting on w, gives me this source term I discussed. So the finite differences of the wave operator q equals m factorial, the unknown potential q, and product of these functions v1 to vm, plus then some error term here, and this error term we can control explicitly. So this is nice because now I have this unknown potential q in my hands, and now I want to recover it. Before I proceed, I need one more auxiliary function. So this function I call by b0. It's another solution to the linear wave equation, but this time it is such that at the end time the values will be 0, so the Cauchy theta at the top of the time cylinder vanishes. And I don't care at this point what are the boundary values. So there are many solutions to this equation, and we can pick our favorite one. So we derive this identity. So if we now multiply this by the auxiliary function v0 and integrate, then we get this kind of new identity. So on the left hand side, I'm just integrating this term, so m factorial q and product of these multiplied by the b0 function, it's a new one. And on the right hand side there would be the box, this wave operator acting on function u, but we can integrate by parts on the boundary. So we can just integral over the lateral boundary of the normal derivative of the solution u. But now we remember that we defined that normal derivative on the boundary is equal to the dn map on the boundary. So this identity now connects the unknown potential q to our measurement data. and there will be some error here, but this we can control still. So right hand side measurement data, left hand side unknown. And now I would be able to recover this Q. For example, if this product P0 to Pm was equal to delta distribution. Because we know that if this here is delta, then Q times delta integrated over the manifold would give me the value of potential Q at some particular point. So that's exactly what we do. So we need now some clever choice of these functions, P0 to Pm, to make this an approximate delta.
So what additional data did you give to the V's? The V you started at the last time, but you have to give boundary data for the V's also, right?
Yes, so P0, so say again?
The V is the auxiliary function.
Yes.
You put initial data at the final time.
Yes, for
You want to solve
P0.
backwards,
Mhm.
and so you need to put data on the cylinder also, right?
Yes, for P0, that's true.
And what did you choose?
I will tell you, so
You haven't done it yet?
not yet, not
Okay,
yet.
fine, okay.
And I have not chosen these functions either yet.
Okay, fine,
Yeah.
okay.
There is some boundary value fj, but I don't not told you what it is yet.
Okay.
Right. So this here should answer the question now. So how to choose V1 to Vm? And our choice was to use something called the Gaussian beams. So you could construct a Gaussian beam by considering one of these light-like geodesics. So light travels along light-like geodesic. Consider one of those. Then it's convenient to parameterize or look at the light-like geodesic in Fermi coordinates. So they are roughly this form. So there is the geodesic parameter S. So basically distance how far you're traveling on the geodesic, and then some orthonormal or orthogonal coordinates which are transversal to the geodesic. So in these coordinates, a Gaussian beam would look roughly like this. But it's not the correct formula, but that's the idea. So Gaussian beam is E exponential to power I times first of the transformer directions times a large parameter tau minus a constant A times tau times the absolute value or modulus of vector y squared. So qualitatively, the Gaussian beams are wave packets traveling on light-like geodesics. So they have exponential concentration on the geodesic, and they oscillate in direction transversal to the geodesic. So if I were to draw a picture, erase this. So here is the plane cylinder picture. So when I send Gaussian beam, it's something that would travel like that. So it's exponentially concentrated on the light-like geodesic, so it travels like light, and then it very quickly decays outside of the geodesic. And there is some oscillation, but that's very small. So that's the kind of solutions that I choose for the linear wave equation. So these boundary values can be chosen so that VJs are Gaussian beams. So now I want to, in my inverse problem, the identity, multiply together these Gaussian beams. And I need at least 4 of them. So in this product I had product from P1 to Pm, and I told you that m is greater than or equal to 4. So I need 4 Gaussian beams. And the reason is that by multiplying 2, I can cancel this oscillating part. So get rid of the stationary phase. It's the reason for the first cancellation. So I choose one of the Gaussian beams to be this one, and another one to be the complex conjugate of this one. So the product of these Gaussians cancels
Along the same, along a different geodesic.
along the same.
The same geodesic. Okay.
So along the same geodesic. So one of them is precisely, let's say this one, and the next, so V2, is complex conjugate of this one. So their product cancels the oscillating part, and I get just the exponential concentration on the geodesic. Then I need to choose a different second geodesic, and there I do the same trick. So V3 and V4 will be complex conjugates of each other along different geodesics. So let's say from here, like that. And now we see that one pair of the Gaussians is supported on this geodesic. The next one is supported this geodesic. So their product is supported here. And here we have just the exponential concentration left. So roughly speaking, this is approximately a delta distribution here. So there we have approximately delta, and that's exactly what I wanted. And the remaining V5 to Vm I can choose however I want, as long as they are supported also here. So this is the basic idea, but unfortunately, since I'm working on some general Lorentzian manifold, these light-like geodesics could in principle intersect more than once. So this picture is not necessarily correct. So the geodesics could have made some turn and intersected again somewhere at a little bit later time. So and then I would get another piece of exponential concentration here. So what I'm really recovering is sum of values of the unknown potential Q at each of the possible intersection points. So this quantity, which was obtained from the measurements of the boundary values, recovers a sum of values of the unknown potential function at each of the intersection points. But I've not yet chosen what is this function V0. So now this V0 makes its appearance. Okay, there will be some error because this is not exactly a delta distribution, so there is some small error, but we can control this. So now I want to get rid of the extra intersection points. How much time do I have?
9 minutes.
10 minutes. Yeah, 5 minutes. Yeah. So I'll just mention that it is possible to choose this function V0 such that if you consider several measurements, several V0 functions, this kind of matrix becomes invertible. So let's look at this again. So here there is this V0 that I've not yet chosen, and here are the values of V0 at each of the intersection points. So if I make many choices of V0, I can write this as a linear system. So it will be a coefficient matrix of V0s at each of the intersection points times the unknown. And this side is the measurement data which I have. So it's possible to choose these B zeros such that the coefficient matrix of the linear system is invertible. And the basic idea is this. So if the black lines here are now the geodesics that I drew here, so I send one pair of Gaussians that way, another pair of Gaussians this way, I have two intersections, then the B0 functions can be chosen so that they pick up the values of the intersection points and separate them. So the first function B0 here travels only through the first intersection point, not through the second one. So this B0 separates this first intersection from the second one. So that's the idea how you construct the separation matrix. Maybe I'll skip this lemma. So the separation matrix can be constructed uniformly. So far, everything here depends on this geodesics that I send, and there are infinitely many points, so I need to send, in principle, infinitely many pairs of geodesics to recover everything. But it's possible to choose these B0 functions so that finitely many suffice to separate any pairs of intersection points here. So it's a very technical thing, but it was necessary for the stability. So finally, we can combine everything. So all the constructions that I did can be done uniformly, independently. As constants are independent of the intersection points here. And if I collect everything, then this error that we make here will be just of Helder type that I showed in the beginning. So it will be measurement error delta to power sigma. And that then recovers the unknown potential Q. And just to emphasize, this quantity here was only known because the equation was nonlinear. So we only do the Taylor series expansion of the solution to the wave equation because of the nonlinearity. So our paper can be found on arXiv. Thanks for listening.
Are there any other questions for the speaker?
So, what happens if you want to consider like a nonlinearities of derivatives? The standard model.
What happens? I think this method still works. So I've not done it. I've not considered it really, but I don't think there is any huge changes.
Are you thinking that if you have a null condition, somehow it might not work with some of these situations?
I don't know. There's some low regularity aspect to it. I don't know.
Yeah, I mean, probably you
So
need
if
to
you
add
have like
some.
if you have like dt phi squared, and then dt phi doesn't work.
Certainly, it's some kind of null condition.
Yeah, you need to make some assumptions, and I made a lot of assumptions that everything is smooth and nicely behaved. But I don't see why, in principle, the approach shouldn't work.
If you wanted to your stability result, but looking at difference of the potentials in a weaker norm like LP, would you improve? Would your power of delta improve?
Oh, that's a good question. I mean, I would imagine so, but even this was somehow a surprise to us, so I don't know what would happen.
I mean, you could try to do exactly what you're doing. Right?
Yeah, so
But look at the difference.
Different norm, yeah. It might improve. If you look, yeah. I cannot say for sure.
So
Very
as,
small. Good.
I was just gonna say, as m goes to infinity, if m gets really big, then you get 4, right? Sigma goes to 4. Wait, sorry. So what am I saying? Sigma goes to 0.
If m goes.
Huh?
If m.
Yeah, if m gets
Yeah.
really big. Yeah.
Yes, I think you are right.
Okay.
Yeah, that would be very highly not
Yeah.
any other problem.
And if m is 1 and it's linear, then you also okay.
If m is 1, then this should fail.
Yeah, then everything fails. So
Yeah,
somehow
something
there's a really good m in between that gives you the best.
Yes, that's true. That's for sure.
This is the, so somehow you don't really use a full digit denominator map, right? You're only sending in very small. So if you had a linear equation, the digit denominator map in any open set determines it everywhere because it's linear, but here it's not. So you actually only use the lambda for very small inputs.
Yes, that's true. Yeah.
But it could blow up. You might not even have a solution, right?
Sure, of course. Yeah, that's right. So this, the condition, your assumption is really for f being small.
Yeah,
So
that's true.
So that's,
Yeah.
where's the picture in the end?
Sorry.
You showed us a picture in the end, it looked really nice. Where's that?
This one.
Niagara Falls?
Yeah, that was Niagara Falls
So you took
3
the
weeks ago. Yeah,
You took this
I
picture?
took this one, yes.
Oh wow. Okay, congratulations.
Yeah, it was really good weather back then.
Let's go ahead and thank our speaker again. So. And thank you all for coming to the in-person incarnation of the Analysis and Applied Math Seminar. We will be going on hiatus for all of the job talks in January and February, so see you back in March probably.
So maybe we should thank the organizers too, Cyril, for